Hello students, welcome back. This is the final video for this unit of energy, and we're going to wrap up talking about conservation of energy in real life, or just applied to situations in real life. Because in our examples, we've just mainly looked at examples where things are falling from high positions to low positions, and their energy is converting from potential to kinetic energy. Okay, in real life, energy still is conserved, but instead of being 100% transformed into what you expect it to be transformed into, a lot of the time energy is dissipated into the environment. Okay, in this example we have an object falling off of a high point to a low point. That object has to pass through all these air molecules between this path. Okay, as the ball passes through a particular space of air, the air molecules there have to move out of the way. So that ball is giving those air molecules some kinetic energy. In other words, those molecules are taking energy away from the ball as it passes through it. And that's also friction or air resistance. Okay, there also might be some sort of sound associated with it falling. Like if it's a small object, or if it's going fast enough, it might whiz through the air, and then some sound energy is released. And there might be some thermal energy as well being dissipated. So in real life, it's not as clean as it is in our examples in terms of the math, but it is still conserved, and the energy isn't being destroyed or anything, it's just being dissipated into the environment. Okay, and I know we've really run this example into the ground, so let's think of something else. Okay, now I want to talk about how the conservation of energy applies to springs. We learned this equation for springs for the potential energy. Okay, this says that the potential energy for a spring is equal to 1/2 kx squared, where k is the spring constant, which is how springy it is, or how strong the spring is, and then x is the displacement from the equilibrium position. Okay, here I have an example where there's a mass attached to a spring. The spring constant is 1.2, and the mass is 7 kilograms. If I were to compress this spring so that it was displaced 0.5 meters from its equilibrium position, then my x is going to be 0.5. Okay, and then at that point, I'm going to be able to calculate the potential energy by using this equation. So I'm going to go ahead and do that now. Okay, so now I have the potential energy is equal to 1/2 times 1.2 times 0.5 squared. I'm going to go ahead and put this in my calculator and figure out the potential energy. Okay, I found with this spring that the potential energy, whenever it's cocked back at 0.5 meters, is going to be 1.5 joules. And I know that whenever that spring is released and it's allowed to shoot back towards its equilibrium position, all this potential energy is going to be converted into kinetic energy as it passes that equilibrium position. Okay, so if I want to find out like how fast is it going as it passes through that spot, I know that all the potential is going to turn into kinetic, so I know that my kinetic is also going to equal 1.5, and then I'll be able to solve for velocity, so let's figure that out. Okay, so now I have 1.5 joules is equal to 1/2 mv squared. If I solve this for velocity, I'm going to have to multiply 2 to both sides, divide n to both sides, and then take the square root of both sides. And then I finally get velocity is equal to the square root of 2 times 1.5 joules divided by the mass, which was 7 kilograms. Okay, I'm going to go ahead and figure that out right now. Alright, I found that the velocity is going to be 0.65 meters per second as it passes back through its equilibrium position. Okay, and then of course, with the spring, it's going to keep oscillating until the energy is dissipated through friction, sound, whatever it may be, and eventually it'll slow down and end up back at equilibrium position. Okay, this then brings me to talk about whenever an object is sliding on a surface, that energy is going to be dissipated through friction between the surface and that object. Some energy is being lost to the heat that is generated from friction. There's a little bit of sound that is associated with the rubbing of two objects. So the energy is going to be dissipated a little bit whenever there's an object sliding against something else. Some substances have less friction than others, like ice. In the case of something rubbing against ice, or something like someone sliding on an ice rink, there is a little bit of friction there still, so eventually they will come to a stop. Their kinetic energy will be dissipated into thermal energy and sound energy. This is going to take longer than it is for something like sandpaper, right? Okay, I hope this makes conservation of energy make more sense. For springs, falling objects, and sliding objects. This wraps up our unit for energy, and the next unit is going to be momentum. Thank you.